In this video, we're going to take a look at the relationship between electric fields and electric potential for point charges and for lines of charge, two common charge distributions. We'll start off by taking a look at our little stick figure friend here who wants to add on to a pile of charge that's already here. So what's the difference between plus lowercase q and plus uppercase q? So plus q, this is our test charge, and we're bringing this in and we want to try and add it to the charge that's already there. Now, this plus q is big enough to change space. Sounds like a real abstract idea, but what happens is that we have this positive charge here, and we know that if we bring another positive charge nearby, it's going to feel a force, and that's the electric force, and that force is going to be directed away from this big charge that's affecting space. So what if this test charge isn't there? Is that going to have, what happens? So we know if we put a charge there that it feels an electric force, but what if that charge is not there? Does that mean that there's nothing different about the location here versus the location here? Because we know if we put our test charge here, it's going to feel a much bigger force. If we go half the distance, then it's going to feel 4 times the force. All right, well, that's where the electric field comes in. This is answering the question, what if our test charge isn't there? And we know the electric force is equal to K little q times big Q divided by r squared, where r is the distance in between the two. So in the absence of the test charge, we know that regardless of what charge we put there, it's going to feel a force. It's very similar to the gravitational field. So the electric field is the force per unit charge. And so for our point charge, that's just equal to K big Q over r squared. And that tells us how Q is going to affect space around it. Now, as I try and carry this charge nearby, as I walk, I have to do work. Work is required. But if I let go of this positive charge, the repulsive force is going to push it away, and off it goes. So when we do work against the electric field, then we add potential energy. So the work that we do in bringing this forward is going to add potential energy to the charge. So the work done by us equals the Coulomb constant times little q times big Q divided by just R and that's equal to our gain in potential energy. Now, if we slip and drop this positive charge, it's going to run away. And just like if we were pushing a rock uphill and we drop it, it's going to roll away downhill. And then it'll lose potential energy, but that loss in potential energy becomes kinetic energy. So if we drop it, so under electric force alone, then conservation of energy holds. So the change in potential energy is going to be equal, or plus the change in kinetic energy has to be equal to 0. That's conservation of energy. which is a cornerstone of chemistry, physics, and pretty much every other science. Right. So the work done by the field is going to be equal to a loss in potential energy, which is equal to a gain in kinetic energy. Great. Okay, so we've talked about energy, but what about this idea of if our test charge is not there? This point in space still has properties that are different than other points in space. And so when we take a look at what a field means, the electric field, like we said, is force per unit charge. And then we also have the electric potential. So force per charge. We do similar things in mechanics when we talk about fluids because fluids are kind of amorphous. And so instead of talking about mass, we talk about density. And then our electric potential is energy per charge. And for a point charge, that's equal to kq over r. So again, this location in space has special properties. If you put a charge there, it's going to feel a force. And then that force, if you can hold it there, it's going to have potential energy. So the force is going to be equal to, and that's a vector, of course, it's going to be Q times E. And then the potential energy is going to be equal to little q times whatever the potential is. And as far as units go, our electric field is in newtons per coulomb, or volts per meter. And our electric potential is joules per coulomb, or volts. And again, these results are point charge only. Now let's turn and take a look at the gravitational analogy. I'm going to share my screen and we'll take a look at a topographic map of Camel's Hump here in Vermont. What you're seeing are lines of equal elevation, and the darker lines are in intervals of 400 feet. So up to the north here is going to be the Winooski River Valley, and we can see this is the summit of Camel's Hump. And if we zoom in really close, we can see some little stream beds. So when the snow melts in the springtime, these little brooks start running pretty quickly. And you notice that the brooks are always perpendicular to the lines, these topographic lines, which are lines of equal elevation, or lines that if you put, say, a boulder there, the boulder would have the same potential energy anywhere along these lines of equal potential. So water is going to flow downhill, and downhill is always perpendicular to lines of equal potential. And then also lines of equal potential give us an indication about how steep things are. So if I was trying to take it easy in ascending Camel's Hump, I'd probably come up this way, or I'd come up on the eastern side. and start off from the state park. And then take it nice and easy because these lines where they're closer together means it's steeper. Now our scale is from here to here is about 500 feet. That's what it looks like. So we have an increase of 200 feet vertically over walking 500 feet. That's pretty steep. But take a look at this part. That's really crazy. So as we zoom in, we can get an actual different scale. Come on. Here we go. Zoomed in a little too much. So these lines of equipotential are very much like electric potential. And the electric field, if this was a charge, is going to be perpendicular to these lines of equipotential. So now let's take a look at a map I did. We have 2-point charges. This is positive 4 microcoulombs, and this is negative 3. And what I did were the lines of equipotential. But you can see that they're pretty radical. So the closer you get, then the lines get really close together. So what might be interesting is for us to take a look at what the contour looks like if we sort of slice this. Right? As an example, we can go and take a look at a camel's hump, and if I did a line north-south to get a profile, well, folks here in Vermont, we're very familiar with what the profile of camel's hump looks like. So we have sort of a back end right here, and then a little bit of a saddle, and then a summit that comes up here and drops off really steeply. So when Samuel de Champlain saw this 400 years ago, he called it crouching lion. And it's very distinct. And in fact, it's on the Vermont state border. So let's take a look at what would happen if we took this and then did a profile. We ran right down through here and then took a look at what the potential was at different locations. And here's what it is. Here's a map. I did a quick Excel graph, and I left out the middle parts because they blow up. In physics, we call this a singularity because when the distance, the denominator becomes 0, then this becomes undefined. So if we were carrying our positive charge closer and closer, you can see it's going to get steeper and steeper, and it's going to take more work for every step forward. But on the far side, it's actually quite easy. So the electric field is actually the slope of the potential versus distance line. And this is showing that the electric field is not very strong initially, but as we get closer, it gets very, very strong. And then as we come down the other side of the hill, it's actually quite easy because we're allowing the electric field to do the work. And then right here, this is where the potential is 0. Now, potential is a tricky thing. We always have to establish a reference point. So we can assume if we took our test charge and went out to negative infinity, then we would be at 0. And as we bring it in, the potential increases. And then after we pass the positive charge, it starts to decrease. And then we approach the negative charge. So very much like the topographic map, a positive charge would be like a mountain. And a negative charge would be like a giant hole in the ground. And so if we allow our charges to just run free, they're going to run away from the positive charge. And again, the electric field is the slope of this line. And then they're going to dive down into this negative region. That's if it's a positive charge. If it's a negative charge, the opposite is true. And so now let's consider what happens when we don't have these mountain peaks. We have something that looks a little bit different. We have a line of charge. I could keep on adding more charges, but I just kind of made these look nice and even. So in green, there are lines of equipotential, and the middle one is approximately 0. And so we have equal charges on both sides, but what happens in this arrangement is that the electric field no longer goes as 1 over r squared. In fact, the electric field gets pretty close to 0 as we get further away from it because the two charges, the two plates look very much the same. And in the middle, you can see the equipotential lines are almost equally spaced, which means our electric field is actually uniform in this region. So now let's go back and take a look at how a line of charge is going to be different. So we'll go back to our worksheet and take a look. And now we're going to take a look at lines of charge. And we'll imagine this to be two conducting plates that are nearby each other. And of course, we know that the way you make something charged is that you move an electron away. So if I take an electron and I move it over here, then that makes this region negative, and it leaves this region positive. Now the first charge comes over for free. It really doesn't, we're not having anything repel it, so it's not too hard. But then as we keep on doing it, it requires more and more work, and that means that we see potential energy starting to build up. And the electric field in between the two plates is uniform. And so we see electric field lines that go from positive to negative. And the electric field is going to be equal to the change in potential divided by the change in X. The electric fields always point downhill, so we put a minus sign in front of it. And conversely, that means that the voltage, delta V, is going to be equal to minus E delta X. And if we wanted to find the work done, well, work is just equal to Q times E, and the potential energy is equal to Q times delta V. This would be the change of potential. So if I allowed charges to migrate from one side to the other, they would theoretically gain potential energy. And this is an extremely common way of accelerating particles. So to summarize, the uniform electric field between plates. So what would this look like if we tried to do a profile? Well, we'd see the potential is going to be pretty close to zero on the outside and spike when we get in here, but then have a nice steady transition. So this is sort of like imagining this slope between two ridges, or say a ridge and a valley, nice straight valley. And then the slope downhill would be pretty uniform. Now, this arrangement is called a capacitor. And because of the proximity of positive and negative charges, they like to stay there. And the Coulomb attraction tends to hold these charges in place. And as you add more charge, the potential is going to build up. So the electric potential and the voltage are going to be similar. So the charge on the capacitor is proportional to the voltage, and we can replace the proportionality symbol with an equal sign if we introduce a value called capacitance. So Q is measured in coulombs, V is measured in volts, and then this new player on the scene is measured in farads, named after Michael Faraday. And this gives us a way of storing energy electrically. So capacitors are used quite a bit in any situation where we're going to have unexpected sudden demands for current. Like in speakers, the bass draws a lot of current. So a capacitor can help a speaker, an amplifier, sound good with bass. Other situations, in a surge protector, you might have a spike of charge on the line, and a capacitor is going to soak that up. And and smooth out the voltage for our electronics that happen afterward. And also we're going to see is they're extremely valuable for timing, but that'll happen later. Okay, well, that's a lot of ground, but hopefully this is helpful in understanding the relationship between electric potential and electric fields for two different distributions, point charges and lines of charge.